This is a simple introduction to cryptography. Here's what we will learn about. First, we'll look at substitution ciphers, especially the Caesar ciphers. Then we'll learn about algorithms and keys. We'll look at cipher disks, modular arithmetic, and then we'll look at cracking simple codes with frequency analysis. Meet Alice and Bob. They are old friends. They met long before last summer. They go to school together. They met Eve at school. She's a new friend. Alice and Bob like to keep secrets from Eve. When they write notes, they use a cipher. They change each letter in the original note with a letter from the cipher. Eve can't tell what they're talking about. Alice and Bob started out with a really easy cipher. Here is how it worked. They took each letter in a message and switched it with the next letter in the alphabet. A became B, C became D, and so on. One day, Bob was homesick. He wanted to tell Alice he had a cold. He didn't want Eve to know first. He wrote a message using their cipher. Then he sent it to Eve's cell phone. Eve got the note, but she couldn't tell what it said. Alice deciphered the message by switching each letter back. Then she told Eve about it. The Caesar cipher is named for Julius Caesar. In this cipher, we shift each letter by 3 instead of 1. So we could call it the add 3 cipher. To encrypt the message, we shift each letter to the third following it in the alphabet. This works fine for most of the alphabet, but what comes after the letter Z? The solution is simple and effective. We just start counting over at A. Eve can't read this note either. We now have 2 different ciphers. One shifts the alphabet by 1 letter, the other shifts by 3 letters. Now Alice has a cold, and she wants to tell Bob about it. She likes ancient Rome, so she uses the Caesar cipher. But what happens to Bob? He expects a message shifted by 1. When he unshifts this message by 1, he gets nonsense. Bob and Alice have to agree, or they can't communicate. This gives our cipher 2 separate parts. The algorithm establishes the general procedure for encrypting or decrypting the message. The key consists of secret information without which the procedure won't work correctly. A cipher disk is a simple tool to help encrypt or decrypt simple ciphers like these. The cipher disk may look like a toy or game, but they were used for military communications as recently as the 1860s. We rotate the inner disk to match ciphertext letters to plaintext letters. We shift counterclockwise to match the key for our own cipher. The outer disk shows the plaintext letters. The inner disk shows the ciphertext letters. The algorithm substitutes one letter for another in the cipher. The key tells us which letters replace which. Since the cipher substitutes one letter for another in the text, we call this a substitution cipher. Alice likes math. She figured out a formula for their cipher. It works by treating letters like numbers. P is the plaintext letter, and S is the key, the letter for the shift. We add the plaintext and the shift to find the ciphertext letter, C. Bob disagrees. He tries it out. he treats the letters like numbers and applies the formula to the add 1 cipher. The letter C should become ciphertext D, but a shift of B yields a ciphertext of E. Alice's equation is just wrong. But in fact, we can't treat the letter A as number 1. Look at the cipher wheel. If the shift is set to the letter A, then the cipher does nothing. A shift of A is a shift of 0. The formula requires that we count letters from 0, not 1. Here's how the formula works with the Caesar cipher. On the cipher disk, we line up the shift value on the inner disk and the letter A on the outer disk. The Caesar cipher uses the unoffset of 3, the letter D. To encrypt the letter C, we add C and D to get 5, the letter F. This one formula tells us most of the story. We can use simple algebra to decipher a message, too. We subtract S from both sides and see that we subtract the shift value when we want to decipher. So encryption is basically adding, and decryption is basically subtracting. Bob has another question. If letters are numbers, and the numbers end with 25 for Z, what do we do? How does the formula encrypt a message like XYZZY? The answer is obvious if we look at the cipher disk. XYZZY becomes ABCCB. But how does that fit into Alice's formula? Alice must use a form of clock arithmetic. That's how we calculate future time on a 12-hour clock. For example, we start a trip at 7 o'clock. We end the trip 7 hours later. But the trip doesn't end at 14 o'clock. It ends at 2 o'clock. The arithmetic wraps around every 12 hours. Let's look at a longer trip. This time, we travel for 42 hours. And of course, there's no such thing as 50 o'clock. We calculate the end time by dividing by 12 and finding the remainder. We arrive at 1 o'clock. In the world of math and cryptography, we call this modular arithmetic. The mod operator says we are calculating with numbers that wrap around. By saying mod 12, we say that our results will always wrap around at 12. We treat our cipher disk like a 26-hour clock. The alphabet wraps around every 26 letters. Alice's formula needs to use the mod operation. And now it works. Alice and Bob are sharing notes and leaving Eve out of the fun. But Eve isn't stupid. She sees that the same text always has the same meaning. If she knows they are using a simple substitution cipher, and she knows what one message says, then she can decode all of their messages. Once she matches a cipher letter to its plaintext letter on the cipher disk, the rest of the letters line right up. But how do we get started? We have a message and no idea what it says. We start with frequency analysis. Some letters show up more often than others in English text. We count the number of different letters in the ciphertext, and the most common letters will show up the most. The letters E and T are the most common in English text, followed by the rest of the common vowels. Common letters in simple ciphertext often encode those common plaintext letters. Here's a frequency analysis of that message. B is the most common letter in the message. E, F, and Q are next most common. We can guess that the most common ciphertext letters stand for common letters in the plain text. Since B appears most often, let's guess that it encodes the letter E. Next, we substitute letter by letter to see if we get readable text. And we do. Thank you for your attention.